So I'm going to talk about complex networks and their analysis in Python language. Let me very briefly introduce myself. My name is Dmitry Zinoviev. I am originally from Moscow, Russia, currently staying in Boston, United States, in the state of Massachusetts. I have been a professor of computer science for the last 20 years. I work in a small university, Suffolk University, which is often confused with the namesake university in the United States. At least I assume there is a namesake university because people often ask me whether I am from the United States or from the United Kingdom. And I have been practicing Python for the last 25 years, and I have been teaching Python for the last 20 years or so while at Suffolk University. In some point in time, I've got very interested in complex networks and the analysis of complex networks, and I became a real fan of complex networks. I'll get back to this point on the concluding slide of my presentation about 20 minutes later. So I thought I'm kind of like um, very excited about distributing the word about complex networks to people who have never encountered them. And I hope I will be able to get you or at least somewhat as close to be excited about complex networks as I am. Um, I am also a pragmatic author, so I wrote a number of books and published a number of books with Pragmatic. The first one is about data science essentials in Python, which already has a chapter on network analysis. This is a pretty old book by today's standards. It's about 4 years old, still usable, but perhaps not 100% up to date. The second book is exclusively on complex network analysis, and I believe it is the book which has been mentioned by Kimberly. So some content from my today's presentation could be found in that book, but there are many other things that are not in the book. Uh, Complex network analysis, just like almost any other technology, evolves over time, and clearly it has evolved over the last 2 years since the book has been published. The third book is about resourceful code reuse. It is not about networking techniques. It is about software engineering mostly. And the fourth book is work in progress. I do not know whether I am allowed to reveal its title. Let me just say that it is a collection of useful Python programming tools, which is expected to be released sometimes in July. I do not know precisely what is the publication date. So I'm going to mostly focus on complex network analysis in Python language. So let me start with a definition, or rather description, of a complex network. What is a complex network? Complex network is a collection of nodes and edges. You can think of it as a mathematical graph with some added properties. Nodes usually represent some kind of objects. These objects could be tangible or intangible. For example, you can have a network of friends, and we call this kind of network social networks, a network of cities, a network of computers, by the way, that would be the internet, or a network of words. Of the four terms that I mentioned, friends, cities, and computers are tangible objects, and words are intangible. And then we have edges that connect the words. We connect to nodes. We connect to nodes if there is some kind of relationship between these two nodes. What is the relationship depends on how we define this network. In a social network, we can have friendship as a relationship. So we connect two nodes if they claim to be mutual friends. Uh, in a network that has cities as nodes, we can have roads as connectors. The network of computers would have wires as connectors. The network of words, also known as a semantic network, use similarities between the words. For example, the words could be synonyms, or they can belong to the same grammatical category. They could belong to the same language. They could describe the same kind of feeling, and so on. So any object that consists of nodes and edges is a network, but not any network is a complex network. Interestingly enough, there is nothing complex about complex network. A network is called complex if it does not have a regular structure. So typically, a network like this, is not considered a complex network because you can simply describe it with a couple of words, say 10 by 10 mesh. A wheel, a network with a hub in the middle and nodes on the periphery, on the circumference, is also not a complex network because it has regular structure. A ring, a network where each node is connected to the next one and then to the next one and then back to the first one, is not a complex network either. So if you can describe a network with a short phrase, usually this network is not considered complex. Anything else, any network with an irregular structure is considered a complex network. It could be as simple as just like half a dozen of nodes, as long as they do not have a regular structure. It is not uncommon, actually quite common, for nodes to have attributes, properties assigned to them. So on top of the mathematical structure, we have some semantic structure. People may have age and gender, cities may have population, computers may have IP addresses, words may have grammatical categories, and so on and so forth. Edges that connect the nodes also may have different attributes. For example, they may be weighted. Some edges may be heavier and some edges may be lighter. So let me show you a collection of different networks represented as graphs. Here is an example of a social network. In fact, this is a network of my Facebook friends, except myself. I am implicitly present behind the screen, so to speak. These are my friends. Every node, every circle represents a person that I know, and I have very strict rules about my Facebook friends. I only become friends with people who I think are really my friends to some extent. And an edge connects to nodes if these two people are also self-declared, self-described friends. So nodes represent people and edges represent friendships. The word friendship here is in quotation marks because um, we understand that many of these people are not real friends. They are friends in quotation marks. They could be acquaintances, they could be co-workers, but in Facebook terminology, they are called friends anyway. So this is a social network. Here's another example. This is ARPANET in 1973, the predecessor of the internet, the original network of 20-something computers. I do not remember precisely how many computers were connected to it. And nodes in this network represent ARPANET nodes. Green and orange, different colors, small nodes and big nodes stand for different types of ARPANET nodes, but overall this is some kind of hardware, and connections between the nodes are communication channels, which are in most cases wires. There is one wireless connection here on Hawaii. I probably won't be able to find it at once. What is more interesting for me as someone from Boston area is that the whole right-hand side of the picture has been located in Boston area, and many of these places like Harvard and BBN and MIT and Lincoln Lab, they are still there and they're still connected to the internet. So this is yet another example of a network. Here's yet another example from my New England. This is a network of airports and airlines. So nodes represent either airports or airlines, and connections tell which airline flies from which airport, or conversely, which airport is serviced by which airline. This is an interesting example of a so-called bipartite network. Airlines are not connected to airlines and airports are not connected to airports, but an airline is always connected to an airport. Okay, and one more example. Interstate migration in the United States of America in 2019. So this network shows how people moved from one state to another. Nodes represent states. So here's my state of Massachusetts, and edges, which are shown as arcs rather than as straight lines as in the previous pictures, represent essential migration flows. In fact, by the end of today's presentation, if you survive, and hopefully we'll all survive, I will show you how to construct this particular network. So at this point, you may ask, why do we need complex networks? What are they good for? There are several reasons why we want to know something about complex networks. First of all, this is a convenient and effective, and I would even say magical way of describing and visualizing complex systems. You may quickly understand the structure of a complex system by looking at the complex network that describes the system. Plus, you will have a strict mathematical description of the complex system. You can use complex network analysis to hierarchically decompose a complex system into parts, into components, and see how these components are connected. You can calculate properties of nodes and edges. I will talk about some of these properties in one of the next slides. And then these numerical properties could be used as either dependent or independent variables in machine learning. Finally, and this is perhaps one of the most powerful applications of complex network analysis, you can perform node clustering and classification. So this could replace k-means clustering or other clustering algorithms. And again, a little bit later, I'll show you why this approach is better in my book. So let me introduce some terminology related to complex networks so that we understand each other's language. A network is called a directed network if edges are directed. They have directions. So rather than saying that A and B are connected, we say that there is an edge going from A to B, which does not imply that there is an edge from B to A. For example, an airline flight is a directed edge. If you can go from Boston to Chicago, it does not immediately imply that you can go back from Chicago to Boston. Perhaps not on the same flight, perhaps not with the same airline. An example would be migration flow. When people move from Massachusetts to Florida, it does not imply they move from Florida to Massachusetts. A network is called weighted if at least some edges have weight. So we do not treat edges just like straight lines, but we think of them as thin and thick lines. Some connections may be stronger, some connections may be thinner. Migration flows would be again an example of a weighted network. So a network of migration flows is weighted and directed at the same time. And if we allow negative weights, a network is called a signed network. For example, a social network that combines friends and foes would be a signed network. Sometimes the relationship is positive, sometimes the relationship is negative with a negative sign. Some more terminology. The degree of a node is simply the number of connections. Then we can define a path in a network. A path is a sequence of edges that starts on one node and then proceeds to another node where the next edge starts that takes us to another node where the next edge starts that takes us to another node until we get one way or another to the destination node. So we've got a path from the start node to the end node. Usually there are many paths that connect two nodes in a complex network. For example, I can see yet another path, at least one more, and one more path. And let's see, there are some other nodes behind the text, so clearly there are many paths over there. If you take the shortest of these paths, the shortest distance that it takes to get from one node to another, we call it the shortest path or a geodesic. A, because there may be more than one geodesic connecting A and B. So we need the definition of path in order to create the whole bunch of network measures. And the most important from social network analysis are the centrality measures, which tell us how central is a node to the network. In particular, when you work with social networks, you want to know who are the most important people, who are the most important actors in this network. You can calculate. In fact, you can calculate it in more than one way. The degree centrality simply counts how many neighbors a node has. And usually it represents the propensity for local impact. Let's say you shout something and your immediate neighbors immediately hear you or see a message on Facebook. And the more neighbors you have, the more prominent is the impact of your shouting. Closeness centrality tells how close is the node on average to everyone else, not just to immediate neighbors, but to the whole network. This usually measures the propensity for global impact. Let's hope that our friends or neighbors in the network are cooperative. So if you shout something, they re-shout it to their neighbors. How long would it take for your message to reach the rest of the network, assuming that members of the network are cooperating. The betweenness centrality measures your propensity for brokerage, controlling the data flows. If you take all geodesics going through a particular node, these are the shortest paths, which means if a node A wants to send a message to node B, it would probably send it through the geodesic because this is the surest way to have the message delivered. If you are somewhere in between, if you are the node SIM, you have, at least in theory, a controlling power. You can suppress this message or you can propagate this message. The more geodesics go through a node, the more powerful is the node. Finally, eigenvector centrality basically says you are who your neighbors are. In other words, tell me who are your friends and I'll tell you who you are. And it usually measures or represents the generalized importance of the node in the network. The same centralities also work for transportation networks, for biological networks, for semantic networks, for any kind of networks. In fact, the beauty of network analysis is that once you construct a network, you don't care anymore to which domain it describes. It still has the same mathematical and programming properties. Some more definitions. The density of the network is how dense it is, how many edges actually belong to this network out of the maximal possible number of edges. Network of density 0 means that we have only nodes and no edges at all. Network of density 100% means that every node is connected to every other node. Node clustering coefficient measures the locality density. How dense are your immediate neighbors? Node clustering coefficient is yet another measure that could be calculated and used as independent or dependent network variable in machine learning. Network structure elements. I only have 20 minutes for this presentation, so I don't have time to go precisely over them, but there are cliques and cores and crust and coronas, connected components, bridges. You can decompose your network into these pieces and make its structure easier to understand. One thing that I want to mention is network communities. A community is a vaguely defined group of nodes that are more connected to themselves than to the other nodes, to the other communities. The measure of community structure is called modularity. It is a number between negative 0.5 to positive 1. Positive 1 means that we have a very nice community structure. We have very well-defined communities, usually visible with an unarmed eye. Negative 0.5 means that there is no community structure whatsoever. It's just one big mess. So here is an example of community. The whole network is at the bottom, and you can easily see there is a blue community on the left and pink community on the right. Community detection algorithms can be used for unsupervised classification. You tell the algorithm, I want the communities, and the algorithm computes the communities for you. You do not even have to tell how many communities you want. Okay, now let's switch to programming side of my presentation. Here is a brief summary of network construction and analysis tools for Python. I do not believe it is comprehensive. It was comprehensive 3 years ago when I just started working on my book. And my favorite module is Network X. If you look at this table, you may notice that Network X is actually not the best of the modules. It is not written in C, which means it is quite slow. A relative slowdown with respect to GraphTool module is about 40 to 135. It is much better now. As I said, this data is 3 years old, but it is still a slow module. It does not have bindings to C and R languages. It is only available in Python. It does not support multiprocessing. It does not have built-in community detection. It does not have built-in advanced layouts. What I love about these modules, it is very easy to install, very easy to learn, very easy to understand. And of course, it is the subject of my book. So when I worked on this module, I realized that it is a gift and I wanted to share this gift with my readers. So the examples that I'm going to give you a little bit later are all in Network X. And of course, it is free. You can download it from networkx.org. So it supports all data structures for graphs, directed networks, networks with parallel edges. It provides many standard graph algorithms, such as computation of all of the centralities, clustering coefficients, cliques, components, and everything else. It has algorithms and functions for analyzing the structure and calculating the variables. It can generate networks. For example, it can generate random graphs with specific properties. It can generate synthetic networks. It is nicely integrated with pandas. If you know anything about data analysis, then you probably have heard that pandas is pretty much the default data analysis tool in Python. So NetworkX is nicely integrated, and it is distributed under BSD license, which means it is free. So the last part of my presentation is an example. I hope you can see this text more or less. If not, then, well, it is always a challenge to put a program on the screen because I don't know what kind of resolution your devices support, but I'll try to do my best. So this is the first part of code that builds the network of migration flows. I import network X as an X. I need matplotlib for plotting, and I need pandas because pandas usually do marvels. You can do the whole thing without pandas, but why if you can have pandas? So I have interstate migration data for 2019 as a CSV file downloaded from US Census site. Then I built a network after reading the data. So basically it says, this is the source state, this is the destination state, and this is how many people moved from that state to that state. And I normalize the data to make sure that all flows are normalized to the range from 0 to 1. I calculate the mean and the standard deviation of all flows. Why? Because I want to get only the essential flows, flows which are above the threshold. My definition of threshold is it has to be above the mean plus the standard deviation. You can have 3 standard deviations here, the 3 sigma. You can have just the mean itself. It depends on your creativity. By changing the threshold, you are going to get either more dense networks or more sparse networks, and respectively, they will have more structure or less structure. So I generate a new graph using pandas data frame as an adjacency matrix. So adjacency matrix basically tells me that here we have sources, here we have destinations, and here is the strength, the width of the edge that connects the source to the destination. Then I set node attributes. I want to know the difference between inflow and outflow because I'm going to use this number for coloring the nodes as potential source nodes and potential destination nodes on the next slide. And at this point, my graph is ready to use. I save it into a file using .graphml format. I can later read it back from this file and do all kind of processing. Let me switch to the next slide. I call function nxdraw, which is the magical drawing tool. I apologize for the quality of the picture. It is very messy. Unfortunately, NetworkX is not the best graph drawing tool. What I would normally do, I would take the GraphML file and load it into Gephi, which is interactive graph processing software. But if I want to stay within NetworkX and Python, this is pretty much the best I can get. So as you can see, in fewer than 20-30 lines, I was able to go from a CSV file to a reasonably readable and analyzable network representation of the flows. Okay, so to conclude, complex network analysis is a powerful data analysis framework that I love a lot. And when you know complex network analysis, everything looks like a complex network, just like when you have a hammer, everything looks like a nail. What you want to do is to look around and see if you can detect any networks around you, that is, nodes connected with some kind of edges. So that's the end of my presentation. I understand that I took more time than I was expected to. Thank you for being patient. If you have any other questions, I'm ready to take them. Looks like we have a question from Elmar. I was wondering if you could speak about edge weight a little more. I am new to this topic. Thank you for the question, Elmar. The weight of an edge describes the strength of the relationship. Let's take a social network. You may be a really good friend with somebody. Let's say you and me are friends since childhood. Then our friendship relationship is very strong. We can assign a weight of 1 to this edge. Now, let's say you also know someone from a conference. You just had a brief talk with that person. Perhaps you even do not remember that person's name, but that person wants to be your friend on Facebook. So you build an edge between yourself and that person, but you understand that this relationship is really very weak. So you assign a small weight to this relationship, perhaps 0.1 or 0.01. Sometimes these weights can be calculated objectively. Sometimes you assign them subjectively based on the feeling on how strong is this relationship. Did I answer your question? Excellent. Okay, so next question is from Ivona. What properties of a network can you use for ML? You can use centralities. For example, let's take the same social network and you know some demographics about people. Let's say you know the gender, you know the age, you know the education level, you know the income level, and you can also calculate the centralities of these people in some social network. And the natural question arises, how are these centralities correlated or not correlated with demographics? Is it true that people with high social standing, say high education level, high income, are central to the network, or are they not? Once you establish this relationship, you will be able, hopefully, to predict where in the network would be a person with particular demographics, or conversely, what would be the demographics of a person in a particular position in the social network. The same can be done with semantic networks, with transportation networks. So usually you use calculated centralities, clustering coefficients, and other measures as independent variables and attributes as dependent variables, or the other way around. Okay, so let me scroll back. Oscar, you are using Python for data analysis. I'm just curious, what are the pros cons for Python versus R for network analysis? Well, you hit me where it hurts. I am a Python person. You may have heard that there is a religious war between Python and R programmers. So I am deeply on the Python side. So um, I would say I would use Python for any data processing task unless uh, it, my life is endangered, in which case I would still go for R. I took a course very long ago on, not a course, but specialization on data science. The course was in R. I had to take it in R because I did not have a choice. But the choice of the language for the final project was mine. So I tried to do it in R. I realized that 1 year later, I still cannot write a single word line of code in R without looking into books. So I implemented the project in Python. I believe since both languages are Turing complete, you can do everything in Python that you can do in R, and conversely, you can do everything in R that you could do in Python. It's just a matter of convenience. Um, Hari, are there any programming languages that are particularly not suited for network analysis? No. You can do network analysis in Python, in R, you can do it in Java, you can do it in C++. In fact, most of the packages that I mentioned in one of the previous slides have bindings not only in Python, but also in Java, in R, or in C++. When performance is important, Python is not necessarily your best choice and R is not necessarily your best choice. Perhaps C++ or Java would be better. Mike, what level of mathematical graph theory should one have to approach networks in Python? Not too much. Basic definitions. You do not need any strong theoretical background. So most theorems from graph theory are not required, and proofs of the theorems are not required as well. In fact, surprisingly, you may find knowledge of linear algebra more appropriate than knowledge of mathematical graph theory, because there are some concepts in network analysis that require spectral decomposition, for which we need linear algebra.
Sorry, Dmitry, I thought I'd be brave and talk a little bit.
Sure.
I have a question on transport data, and if I'm interested in kind of transport and trying to get any project done, would you have any kind of resource that I can go to start kind of learning on the specific application of network for transport
What do you
related?
mean by transport?
Let's say things like city transport in a city, for example, or between cities.
You mean transportation?
Yeah.
Um, Network analysis has been used very heavily with respect to transportation systems. In fact, there was a great project about a year ago supported by the state of Massachusetts where they studied Uber flows, like how passengers move from one neighborhood to another using Uber. And they built a network of Uber flows in the spirit similar to the one of interstate migration exercise. And I do not believe there is any book or any specific site on the subject. But if you Google research papers using Google Scholar, you would probably find a couple of dozens of papers on the subject. Um, there is a researcher in Italy who is very heavily using network analysis to transportation flows. Her name is I forgot her name. If you drop me your email address, I will send you her name. Fosca is her last name. Fosk. I'll put it in the chat window. John something. Fosca. So if you Google her name, you will find a couple of her papers on this. So I would say if you take a basic course in network analysis based on my book or based on something else, there are some courses on Udemy, there are some courses on Coursera, and then read a bunch of specialization papers, you would be in a very good position to do this kind of research.
Thanks very much, Dimitri.
Yeah. Thank you very much, everyone. It was exciting. I was very excited to have so many questions.